I'm one of the 18 to 19 Blue Waters Fellows, and I'll be talking about work today that I'm doing on source processes of intermediate depth earthquakes. My advisor at Stanford University is Greg Broza, and much of this work was done in collaboration with Yongfei Wang, who it has a joint appointment between San Diego State and University of California, San Diego. So I use Blue Waters to simulate intermediate depth earthquakes. And so some of you may be wondering, well, what are intermediate depth earthquakes and why do they matter? So I'll try to convince you that they do matter and you should think about them. This is actually just a figure showing the distribution of all earthquakes in the world as you go deeper in depth. And intermediate depth earthquakes, if I had a laser pointer, I'd shine it at that little dip in the middle there. They're actually less than 1% of the global population of earthquakes. So now you're really thinking, why do I really care about them? But they're kind of interesting to think about because at intermediate depths, which is, sorry, that should be 70 to 300, I missed a zero there, 70 to 300 kilometers, because at that depth you have really high temperatures and pressures. And so the pressure is really high, you need to overcome really high frictional strength, and the temperature is very high, so the flow stress is low. And you would expect that if you were to apply a shearing force onto this rock, it might just deform ductily instead of actually break. And when you model an earthquake like a shallow earthquake, normally you're just modeling a crack opening as in solid mechanics, and that's a mode of brittle failure. And that kind of physics is just not enabled at those depths. So we need a different mechanism to explain how they nucleate. And so this is actually one of these proposed mechanisms. It's one of the more well-established hypotheses that's been around since around the 80s, which is that at those depths, there's actually some kind of dehydration reactions in the rock that release water that goes into the pores, which increases the pore pressure, and that reduces the effective frictional strength of the rock. But there are other proposed mechanisms for how these earthquakes occur. For example, there could be the generation of thermal shear instabilities. So that's actually a form of ductile deformation, but it's an exothermic reaction. And when you get a little bit of shearing on the rock, it heats up, and it heats up faster than the heat can diffuse away, so it will start heating up rapidly, and then you'll get some kind of rapid slip that looks like similar to a brittle earthquake when you're recording it from a seismogram on the surface. And so those are two of the common mechanisms that people have proposed from doing analytical analyses and lab experiments in the past. But how do we really compare what these hypotheses to the data? Some of the challenges of actually looking at intermediate depth earthquakes and trying to verify possible mechanisms from the data are that the data is kind of scant in comparison to other earthquakes. And remember that you're looking for 1% of the world's earthquakes that come about 150 kilometers deep, so it's also harder to record them. And hence, if we are actually trying to do an inversion of their source, we usually don't have very good resolution of what they look like, so it's a really non-unique problem. And actually, a proper physical model for how these earthquakes nucleate doesn't really exist. And I have the word data inversion there, but maybe a better term would be data analysis, because even things that people do, like try to calculate the energy release of these earthquakes, is based off of assuming simple models that are based off of what we know about the physics of shallow earthquakes. So it's kind of like using a circular lens to look at something that's really quite multidimensional. So how can we incorporate actual hypotheses about how these earthquakes nucleate into numerical modeling and tie these into data? And another thing we're interested in looking at for these earthquakes is how they change from small to large scales, because in general, the physics of shallow earthquakes tend to suggest that shallow earthquakes are self-similar, but a change in this behavior would represent a departure in the physics. So this is actually a study that I've recently submitted, which is looking at the change in the change of stress for small to large intermediate depth earthquakes. And we found that there's an apparent non-scaling, but if you look at like towards the bottom of the graph are the smaller earthquakes, and towards the top are the larger earthquakes. And the higher you get, it's harder to study these earthquakes using the same circular model that we've been using to study all the smaller ones, because this kind of circular approximation breaks down as you get into larger earthquakes and more complexity. And so just to give you kind of more of a real world example, there actually are really large intermediate depth earthquakes. So this is also why you should care about them. So I actually took this picture from a Scientific American article, which stole this figure from the USGS shake map. And the author of the article kind of, what is that word? Contentedly said that these earthquakes are not much of a worry because it's like setting off a bomb in a mine instead of setting off one at the surface. But if you have an 8.0, this was fortunately in a relatively uninhabited area of the Amazon rainforest, it's still going to cause damage. And last year there were about 2 magnitude 7s, which were intermediate depth earthquakes in Mexico. So those did cause some damage because they didn't occur in the middle of the uninhabited forest. And furthermore, because these earthquakes aren't on actual known and mapped faults, it's kind of harder to know like where exactly they'll occur, or if there's like a recurrence model for them, because they're not really like on faults as shallow earthquakes are. And in addition, their spectra could look different from shallow earthquakes, and those are essential to, as in was mentioned in a previous talk in this session, for understanding ground motion for, say, engineers. So blue waters can help us run dynamic rupture models to study larger intermediate depth earthquakes with more realistic physical models. And so these are some details about the code that we use to run the dynamic rupture model. We use SWORD, which is short for Support Operator Rupture Dynamics, and that's a staggered grid split node code that was written by Jeff Ellie and Stephen Day and some people at UCSD. And Yongfei actually recently modified our version of the code, which we're using, to also include hybrid OpenMP and MPI. So that's a new thing that was added to Blue Waters, I think, recently. So we did so this is a dynamic rupture simulation of an earthquake that we did in southern Japan in Kyushu. So it was a 2006 magnitude 6.4 event in Oita Prefecture, 145 kilometers deep. And this is probably the only dynamic rupture simulation of this earthquake ever. And I thought it was kind of interesting because there's almost no seismicity in this region at all, but about 10 years later, there was the really huge Kumamoto event in almost the same region, but that was a shallow event. So we don't really know much about earthquakes in this region at all. And so what I'm showing here on the right-hand side is basically the slip on the fault due to the earthquake. And what's interesting about this earthquake is that the rake, so the direction of the slip, is actually changing throughout time. And on the right-hand side, you see the actual slip contours. So like it could be confusing because you see the red dot in the middle and you think that, oh, the rupture started there, but that's actually the area that was most stressed. So that's released the most energy as it broke. And the rupture actually starts down where the star is, and it goes off over time. So it's a really complicated rupture. So that really gets into what we're talking about. We can't really approximate these as circular models. So if we were trying to calculate the energy release from them using a circular model, we would be grossly miscalculating what that is. And then so this is kind of the same idea, but as a snapshot over time. So at the end of this presentation, I'll show you the actual movie because this is a PDF. And so that's what we've done. And so kind of moving on to what we're doing now and future research is that this process could be improved. This is a figure I kind of took from the SCEC rupture validation project, which explains how the workflow that goes into making dynamic rupture models. And one thing that we're really actually interested in modifying is that little box on the far right hand, which is the fault friction. Because if you remember these things I was talking to you about at the beginning, well, these all suggest that there's some kind of dynamic weakening mechanism at play in generating these earthquakes, which means that during the rupture itself, the friction is actually changing, and it's changing non-linearly. But for so this is the actual friction law that's used in the support operator rupture dynamics code, which is the slip weakening friction law, and it's illustrated on the left-hand side. For most rupture dynamics codes, because of computational complexity, it's generally just okay to use something that's linearly weakening over time until you get to dynamic friction. But we're actually interested in looking at different friction laws that better approximate some of these mechanisms that we're actually trying to propose. So one possible mechanism, which is kind of similar to the thermal shear heating mechanism that I proposed at the beginning, is this kind of thermal pressurization method in which you have a coupling of temperature and pressure equations as your fault heats up over time. It's also increasing the pore pressure. And so that is a kind of dynamic weakening mechanism that decreases the frictional strength non-linearly during the propagation of your rupture. But if we were to actually solve these equations at every node, at every time step, it would be kind of a computational bother. It's also possible to just approximate the old friction law, which is the one that we have coded, which is the slip weakening friction law, but using a nonlinear slip weakening distance. So it's this constant we have in equation 1 here. So this is like the only 3 equations I'm going to show in this talk. But anyhow, the main idea is that we're able to approximate this very computationally intensive friction law with a slightly less computationally intensive one that's still more computationally intensive than the one we were using. Sorry, that's a lot of uses of the word computationally intensive. But basically, the idea is that if you remember this story about the blind man and the elephant, well, before we had a bunch of like maybe spherical models, and we're trying to build something like an elephant out of spheres. But if we use slightly more complicated friction laws that are more similar to the physical mechanisms we're trying to propose, then maybe we've equipped ourselves with something else like a fan or a rope, so we can better describe what an elephant actually looks like with some tools that look more like the elephant. So in summary, we use blue waters to simulate a large intermediate depth earthquake, which has a complicated rupture, and currently we're looking at implementing alternative friction laws to better approximate the actual mechanics, which are hypothesized for intermediate depth earthquakes. And blue waters allows us to study larger intermediate depth earthquakes with better incorporation of physics, and we hope to maybe extend this analysis to more intermediate depth earthquakes, especially ones that have been happening recently. And I would really like to thank the NCSA and the entire Blue Waters team for giving me this opportunity, and Scott Lathrop and Ryan Mokos was my point of contact, but he's not here, but I'd like to thank him too. And everyone who answered my JIRA tickets, some of which were probably really dumb, but thank you for putting up with me anyways, and all of you for sticking around. So here is a slightly cooler version of the picture that I showed on my slide. And then you can really see how the rake angle is changing as the rupture propagates.